Hopefully my microphone is working here. If anybody's watching what's going on, please let me know if any audio is messed up. I guess I'll start in a minute here. I'll give my little spiel that I usually do before I do anything. I decided to do this based off of one of the suggestions in the survey that was sent out this morning. I realized that some of these problems in section 3.2 are pretty difficult, and most of the people, by a slim margin, I think I got 22 votes on my poll. 12 of you wanted to go over 3.3 on Thursday, and only 10 of you wanted to do 3.2 again. And so I want to give a chance to some of you who wanted that 3.2 material to be put out there to see how those problems are done. Of course, the catch to that is I have no idea who is even going to show up to this, if anybody would even show up to this. If nobody shows up, that's totally fine. I'll just sit here and solve problems, and then I will upload it to my YouTube channel, and you guys will have that to watch. But otherwise, the chat is completely open. You don't have to. You can log off, use a different YouTube account. You can be anonymous if you want. You can ask me any questions. Otherwise, I'm going to go ahead and start solving some problems, and yeah, that'll be that. So I'm going to start recording. All right, so this is going to be a series of graphing rational functions problems. I will do problems in the order that I want, unless I have a request otherwise. I will, of course, take requests. So let's take a look. And by the way, you can scan the QR code that's at the top of the screen if you want the packet I'm working from. So I guess the first problem I'll start out with is the problem that we did in the session. Now, this is a worked example in the packet, so I do have a video on this problem, but I think it's a really good example just to go over again because it's pretty straightforward. It's pretty easy to see what's going on. So when we're working on these problems, you want to keep in mind the order of the things we want to go through when we're doing this. So on the packet I released, again with the QR code, I give that list of things you got to do, and all I'm going to do is I'm just going to go down that list, and I'm going to start filling in the information, and then I'm going to use that info to actually draw a graph. So step one says to factor p of x and q of x, but this is already given to us. This polynomial, or not polynomial, this rational function is already in factored form, so we're good on that step. The second term is to cancel anything that we can. So we can actually cancel terms in this situation. So this term x plus 1 will cancel from the numerator and the denominator, and anytime a term cancels completely from the denominator, so it might be left over in the numerator, but as long as it's left, or as long as it's completely taken out from the denominator, this then becomes a whole. So the whole in our graph occurs at x equals -1, but we want to actually find the y value of this whole to find out where it's going to end up being. So we take that x value and we can plug that back in to the function. So if I plug in x equals -1 into our function, and let me actually, I guess I should have done this first. Our simplified version of the function will look like this, right, after cancellation. And so when I plug this x value into a function, or into the function, we are going to get that, well, -1 and -1 is -2, and then -1 plus 2 is, +1, and then that is going to equal -2. So the actual point that the whole is going to reside at is going to be -1, comma, -2. Okay, so the next thing we want to do is we want to, I already did that. Now we want to solve for the numerators and the denominators. So if I want to find the zeros of the function, I take my numerator and I set it equal to 0. And in this case, because we've taken care of the wholes, we can actually work purely based off of the new function that we factored and reduced, right? So I can actually just work off of this function right here. And so when I set that numerator equal to 0, I pretty simply get that x equals 1. And then if I set my denominator equal to 0, that's not the symbol I wanted to write. That's not the symbol I wanted to write either. VA, there we go. If I set my denominator equal to 0, I, again, pretty easily find that x equals -2. So I have zeros, I have asymptotes, but let's keep going. I then want to find horizontal or slant asymptotes if they exist. So there may not be a horizontal asymptote, but there could be a slant asymptote. So we want to see what the situation is. And for this, what we want to do is we want to look at the degree of the numerator and the degree of the denominator. And we're going to compare them. And so in our case, the degree of the numerator is 1. That doesn't really look like a 1, but the degree of the denominator is also 1. And in this specific case, because we have equal degrees, we then want to look at their coefficients. And their coefficients, of course, are also both 1. And so in this specific case, we divide those coefficients, and then 1 over 1 is simply 1. So we get y equals 1. Now we want to set x equals to 0 and solve for y-intercepts. So if I let x equal 0 in my function, we get, well, here, I'll do it more concretely. We get 0 minus, and let me scroll down just so things aren't being blocked. We have 0 minus 1 over 0 plus 2, and this is going to become -1/2. Okay, so now that we have sort of all this information that we could ever want, I mean, not really, but we have all this information, we're gonna make a sign diagram out of everything we've done thus far. And so let's start by just drawing out my sign diagram. And now what we want to do from here is we want to mark down asymptotes, we want to mark down zeros, right? So asymptote at -2 gets marked here. 0 at 1 gets marked here. And it can be helpful to actually mark down which points are which, because it will sort of help with the analysis. It's just a good habit to get into. And then I can analyze the terms. So both of these terms came from positive linears, so I can draw straight lines like this. Then I'm going to pick my sample points. Hopefully we're getting better at this, but you can stop me if I'm going too fast. This interval right here is going to get 2 negative values, multiplied together become a positive. This interval right here get a positive and a negative value, so that's negative. And this interval right here gets 2 positives, so it's a positive. Okay, now this is where the hard part sort of comes in. We want to combine all of this information and turn this into a graph. So what I'm actually going to do to kind of give myself room is let's make this smaller, just so I still have the info, but I want some nice space to draw my graph here. So, okay. Hopefully that's not too small. Yeah, I think that's still readable. Okay, so let's draw our graph. So, have our axes. Okay. And let's add just a few tick marks for now. We can always add more if that's not enough. Okay, so before I even start drawing, let's just write down all of the information that we just spent time discovering, because, you know, we didn't do that work for nothing. So I have a hole in the graph at -1, -2. So right here, I'm going to draw an open circle. We have a vertical asymptote at x equals -2. And I'll actually draw this in yellow, just so we know that this is an asymptote. So, okay. This line's not going to be perfectly straight, but I'm realizing that my axes aren't perfectly straight, so you'll have to forgive me for that. Then we have a horizontal asymptote at y equals 1 going across the center. And what else do we have? We have a y-intercept at -1/2. And I forgot something. Oh, my 0 is at x equals 1. That's right. Okay. Now that I have all of this information, I want to try and draw a graph. So let's take a look at each interval on my sign diagram, because that'll tell me where that function lies, and then we'll kind of go on from there. So my first interval from negative infinity all the way to -2 is going to tell me that my function has to be positive. And so let's think about what this means. We want our function to avoid touching the asymptotes. And so this function, let's start it over here on the positive side of the horizontal asymptote. Now, I'm going to draw it first, and then let's see why I picked what I picked, right? So I'll start it above the horizontal asymptote, move it closer, and then kind of as it reaches that vertical asymptote, it's going to shoot off towards infinity. Now let's think about what would have happened if I would have chosen this initial segment. And here, I'll do it in a different color just so I can show that's my example. If I started with this initial segment of my function, because so far I haven't broken any rules yet, it's still positive because it's above the x-axis, and it's still using that asymptote as a guide rail. So if I keep continuing this forward, I'm going to run into an issue because I don't want to cross that vertical asymptote, and I can't cross the x-axis because I can only cross the x-axis in a place where 0 occurs. And because no 0 is occurring in this part of the graph, I know that my function can't actually be in that spot, if that makes sense. So let's go ahead and draw out what that might look like. How do you know if it passes the horizontal asymptote? My professor said it can pass through the horizontal asymptote, but not the vertical. Yeah, that's actually a really, really good question. I think I have one question in this packet that actually shows that off. I can try and pick that to go over next if you want to see how that looks like. But right off the top of my head, so okay, let's briefly talk about this, and then I'll return to the problem. So let's say I have a graph, and I have some function, but it has a horizontal asymptote. And just for this example, I'm going to place my asymptote just across 0 like this. So keep in mind that underneath this thing, I have my axes, right? Okay. So the thing about horizontal asymptotes is, yes, you can cross a horizontal asymptote, and there will usually be a couple of indicators telling you that you can. The important fact to remember about horizontal asymptotes, and I guess this holds true for vertical as well, but the special reason about vertical that makes you never be allowed to cross them is that they're an unincluded value from the domain. So we're not allowed to cross those. But for a horizontal asymptote, let's think about a case where we might allow this. Case number 1, if you have a 0 that lies on a horizontal asymptote. So let's say you had a horizontal asymptote of y equals 0, and one of your zeros ends up being like right here. Your function has to pass that at some point, but it can still follow the behavior of approaching at infinity. So what this might look like, if my blue line is my function, is maybe, and I'm just making this up, this is not anything concrete, maybe it starts from this end, sort of travels in, it gains some height, and then it crosses through like this before going off. Whoa, I just deleted it. There we go. Before going off to infinity again. It can go through 0 because we have, it can go through the asymptote because we have a 0 at that point. Other indicators that might let you know this is like if the sign diagram is passing through positive to negative and there's no way that you can kind of like pass through. So yeah, the two indicators would be the sign diagram can tell you and the zeros can tell you. And I'll try and pick the example that I think shows this off next, but hopefully that answers your question. I'm going to keep going on, but if that didn't answer your question for any reason, just let me know. So let's get rid of this guy. Okay. So let's continue graphing this function. What we want to do next is we want to look at the other intervals. So we have, just give me a moment. So we have an interval on the sign diagram that's negative and an interval that's positive. And so between -2 and +1, I need to stay negative. And so I'll start down on the vertical asymptote using that as a guide rail, moving upwards, crossing my, oh, that is way too steep. Okay, hold on. Let's draw this more accurately. Starting upwards, crossing this point, crossing this point, crossing this point. And then from 1 to infinity, I know that I have to stay positive, but I don't want to cross that asymptote because I need to approach that at infinity, right? So I can keep moving on like that. So that is an initial example. Hopefully that made sense. Speak now or forever hold your peace, but I'm guessing no one will speak because that was a pretty easy example. So let's go ahead and move on to another problem. And I will try and pick the next problem. So unless someone wants to pick a problem from the worksheet, I think what I might do is I might go over, I'm going to briefly check and see if this has the behavior that I want. I just want to make sure this is the example that I want to go over. Okay, yeah. So this next function I'll go over is going to have the behavior of a function passing through a horizontal asymptote. So let's see what that looks like. So the next function we're going to do is f of x equals 4x over x squared plus 4. Okay, so how does this work, right? We are going to need to go down that list and find a whole bunch of bits of information, right? And so let's start doing that. Step number 1, can we factor the numerator or the denominator? In this case, it's no. We actually can't factor either. It might be tempting to try and factor this guy, but that's actually not going to work out, and we'll kind of maybe see why in just a minute, so I'm going to hold off on that. So no terms will cancel, so there are no holes. So we have no holes in this graph. But the next thing you want to do is you want to set the numerator equal to 0 and solve for the zeros. So if I find my zeros, I could set 4x equal to 0, and that simply gets me x equals 0. My next task is to find vertical asymptotes, and so I can set this guy equal to 0 and solve. And then this is where the interesting thing happens, right? So if we take a look at what happens if I set this equal to 0 and solve, if I try and subtract my 4 and take my square root, I get the square root of a negative number, which is heavily discouraged in this course. I mean, we're just simply not going to treat this as a real answer. The other way you can imagine this is graphically. If I have a graph of x squared plus 4, that'll look like a parabola raised 4 units upward. There's no way that thing is ever going to intersect the x-axis. It's just not going to happen, right? So in that function, we know that we have no zeros, and so we actually have no vertical asymptotes either. So for vertical asymptotes, I can simply say none. There are no vertical asymptotes. Okay, what else do we want? We're going to find horizontal asymptotes. So how do we do that? Well, the rule we have here is that we're going to look at the degree of both. So the degree of the numerator is 1, and the degree of the denominator is 2. In the case where the numerator has a smaller degree than the denominator, our horizontal asymptote is automatically y equals 0. And so that just follows from the rules. If you were kind of unsure on how I did that, you'll want to check theorem. I don't have it up right now. I just want to find what theorem it is. You'll want to check theorem 3.3. No. Yes. I think 3.3. 3.3 or 3.4. It's one of the two. That'll have the information about horizontal asymptotes. So it's going to be y equals 0 automatically. But let's keep moving on. We want to set x equals to 0 and solve for the y-intercepts. So we know that if I set x equals to 0, I get 4 times 0, 0 squared plus 4. This is equal to 4 over 4, and this gets me 1. So my y-intercept is at 0, comma 1. And what else? Okay, we want to make a sign diagram. Okay, so what we'll notice is that in the creation of this sign diagram, what's going to happen, right? So we have one point to put on our sign diagram, and that is our 0, right? So I have a 0 right here at x equals 0, actually, right? And that comes from a positive linear term, so I can place that down. And you might be thinking, how do we handle the case of our parabola? Well, remember what I showed earlier, that if we draw that graph, we have a parabola 4 units up that never intersects the axis. But even more than that, it's always positive, right? This value is always positive. This value is always positive. Can I ever get a negative value by taking a positive plus a positive? And the answer is no. So because I'm going to be contributing purely positive values, I don't need to even include it in my sign diagram. And so my sign diagram quite simply just becomes negative, positive, like this. So, okay, let's go ahead and make this a bit smaller, just so I have room to make my graph. And let's see what this thing is going to look like. Okay, all right. Got plenty of room here. Let's draw my axes. Okay. And then, let's see, I can probably get away with not too many tick marks. Let's just try 3 again. I try and give you guys problems that aren't going to be too crazy computation-wise. But, okay. So, what are we looking for here? Let's start graphing our values. So I get a 0 at x equals 0. I'll make it nice and bold. I get a no vertical asymptotes. I have a horizontal asymptote at y equals 0. So that's a little higher than I want it to be. Okay. Horizontal asymptote at y equals 0, and I have a y-intercept at 0, comma 1, right? Okay. So how do we draw this graph? Well, hold on. Did I get the calculation of my y-intercept wrong? Because something feels incorrect here. Oh, yeah, sorry. I did get it wrong. Quick correction. The y-intercept is also going to be 0. So let me erase this point I drew. Y-intercept will also be 0 because for some reason I didn't realize that 4 times 0 equals 0. And then if you just take 0 divided by anything that's not another 0, you'll get 0 back. So yeah. Our only intersection, x-intercept or y-intercept, is at the origin. So now I'll draw the function blue. We want to follow the rule of the sign diagram while playing nicely with the horizontal asymptote. Now, as Amelia in the chat just mentioned, we can sometimes cross the horizontal asymptote, and that's okay. The behavior we're concerned about happens at infinity, not necessarily locally. When I say locally, I just mean near the origin, right? So we need to start negative by our sign diagram. It's kind of covered up by the chat, but let me move it there. So we want to start locally by that sign diagram, or start negative, sorry. We're going to start traveling in close to the asymptote. Now, I need to have an intersection with the graph at the 0. And then after I make that intersection, I need to be positive for the rest of forever, right? So I can start kind of drawing a bit of increasing, and then I can do this sharp decrease and slice through that point, kind of make a bump like this, and then continue traveling out towards infinity. And as you can see, this has maintained the rule of being positive around, or sorry, being negative before 0 and being positive after 0. Now, a question I might anticipate somebody asking is, how did I know that I have these little humps here? Well, I'm going to give you an answer that's not going to be great either way. One thing is that we actually would need calculus to find out exactly the behavior of those humps, and that's beyond what we do in this course. However, you can sort of think about it like, if we didn't have those humps in those spots, the function would look really, really weird. And let me just explain what I mean really quickly. If I had that same graph, and I'll just draw it very quickly, with an asymptote across the center, okay? If I start in the negative the negative portion of the graph, that's all I'm trying to say. And we know I have to cross the origin at 0. If I start traveling this way, and I never increase at all, it's going to look very odd how I would do this. And I'm going to have to go like this, kind of. I don't know. It's going to look really awkward. Essentially what you want to get used to is, and again, this just comes with practice, but functions around asymptotes curve a lot. And so if you're drawing a jagged or like a line that hugs an asymptote completely, especially near the origin, that's a good sign you're doing something wrong. You don't want to have weird behavior like this. That is not, like, functions don't make sharp turns. They don't make jagged arrows. They're very nice and smooth. They look very aesthetically pleasing. I don't know, to put it a certain way, right? So you want to be careful with what you're doing in that function. Okay, so that is a more clear example on how to do that example. Let me look at another function that I could maybe go over. I'm also willing to take some examples in chat. Actually, I want to take this opportunity to move this just because I want to steer clear. There we go. Not that the chat is particularly popping off right now, but that's okay. Just want to make some room for everything else. Okay, so let's look at, it's kind of hard to imagine what these look like off the top of my head, but I want to see if I can choose a more interesting example. Alright, let's do, I'm trying to think about what we didn't get to last time. Let's try this one. I'm going to do number, if anybody's following along in the packet, I'm going to be doing number 5. So let me add a page, and this is going to be, oh, we're using fancy variables now. Okay. R of z equals z over z squared plus z minus 12. Okay. How would we do this one? Well, I'm just going to keep going through that list of steps and see what I can do. So, graphing rational functions, first thing to do is to factor p of x and factor q of x. So we actually can factor in this case. Z is going to be left alone because I can't just factor a single term z, but I can factor this, or at least I should be able to. So if I think, well, I need two things that multiply to negative 12 and that add to positive 1. So I think negative 4 and 3 should work. Let's see. Would you willing to do a problem that is not in our packet but one I did in my notes with the professor? Yeah, absolutely. If you want to send me a problem, I will absolutely go over it. If it exists in the textbook, you can give me the page number and the problem number. It might be a horrendously difficult problem, so you might need to bear with me, but I'm totally willing to give it a shot. Yeah, totally drop a problem in the chat and I will go over it. Yeah, I'll give you a second to find that problem. I am melting in my room because I cannot turn the fan on without blowing out the microphone, but you know what? I will do anything for my four loyal pre-calc viewers right now. I don't know. I didn't expect to get a huge crowd, but I'm glad that at least a few people are watching, who are hopefully not my friends downstairs. Okay. Let me just pull up the textbook. Graphs, rational functions. This is actually, well, thank you, Madeline. I'm very glad that you are enjoying the stream. Make sure to like, subscribe, donate. No, I'm kidding. Don't do that. Please don't subscribe to my YouTube channel. You do, trust me, you do not want the notifications when I do test streams and you get like 5 notifications of me messing around with my streaming software. Let's see. Okay, Amelia, I will wait for you to drop something. However, I think I see like some other interesting examples that might be good. Like, you got to do some more work for them, but I will of course let you put something in. Here's actually what I'll do. Let me see. Let me try. I know sometimes the textbook problems aren't very forgiving, and I try and choose the forgiving problems because I don't want to just sit at the board for an hour, but I will write down a problem to do next, and Amelia, please feel free to drop a problem if you want. I will just start something. Let's see. Let's try this. Hopefully this doesn't get too ugly. Sorry, I should write the function title first. I need to zoom in. This is really... Okay. G of t equals 3 minus 5t minus 25. That's a scary number. It's a very big number. T minus 9. Okay. And so the reason that this is complicated is because this isn't quite a rational function yet. So sometimes you'll be given a function that looks interesting and you kind of need to do some work to actually get it in the form that you want. So let's see what that will look like. Give me 2 seconds to adjust my okay. Oh, page 233, example 3.2.2. Okay. Sorry guys, my my hotkey for switching to that title slide is 2 on my number pad. So okay, 233, example 3.2.2. Okay. I wonder. 233. Oh, sorry, I'm 10 pages behind. I was looking at 223. Okay. Oh my, you are real. You're really gonna test me on this one. All right, that's totally fine. Okay, so let's go over it. The question, I'll write it down for you guys really quick, is G of t. Oops, let me switch to this slide. G of t equals 2t squared minus 3t minus 5, and that is all over t squared minus t minus 6. Okay. All right, so let's see how this is going to work. So, again, this looks like a scary problem, and, you know, would I be lying if I said I was scared? You know, right, maybe I would be. But, all we're going to do is that list of steps that I lay out on that packet, I'm just going to go through and do every single one of them. Now, they may be more difficult in some cases than the other, but we're still going to do them, right? So, scary part number 1. You need to factor p of x and q of x. So, I'm going to try and write this function out with a fully factorized form, right? And so I'll give myself plenty of space to do this. I'll even do it in color. How about this? Looks very nice, right? Okay. How do we factor this guy? Okay, so let's really hope I don't need to pull out the quadratic formula. Let's hope this is factorable. I'm going to do the AC method. So I can take my A value and multiply it by my C value. Now, from this point, I can factor normally. So I need two things that add to -3 and that multiply to -10. So I typically would want to think, okay, well, what multiplies to get 10? Okay, well, 5 and 2 multiply to 10. How can I combine 5 and 2 to get -3? Well, if I had, say, -5 and +2, I could add that to get 3. So I'm going to choose -5 and 3. Or sorry, -5 and 2, because, right, -5 times 2 equals -10, and then -5 plus 2 equals -3. So that should work, right? So I should be able to then take this and go into t minus 5, t plus 2. And then from this point, what we want to do is we want to, this is like the really weird step. You want to divide your constants in those factors by the value of A we multiplied out earlier. So I would write this as 5/2 t plus 2/2, but that's just going to be 1. So 2/2 is just 1. Now, something we can do to make this look nicer, and I guess I'll do now just so we have it in a nice form, is because I can set this term equal to 0, I can actually multiply it by anything I want to simplify. So I will simplify by multiplying by 2. I get 2t minus 5 because the 2's cancel, and then that's my new factor. And so what we end up getting in the final answer is that this thing equals 2t minus 5 times t plus 2. Or I'm so sorry, t plus 1. So hopefully that makes sense. I'm going to make this guy smaller, so it'll still be on screen. It'll just be a little, and by a little I mean a lot, smaller. But I will write down the factorized version. So this should be 2t minus 5 times t plus 1. Okay. Then at this point, we want to go ahead and just factor the denominator. So right, we're still on step 1. It's taken us quite a while, but we're still in step 1. We factored p of x. That's our numerator. Now let's factor q of x after I take a drink of water. Okay, so q of x is t. Sorry, I want to be color coded. Okay, q of x is t squared minus t minus 6. So I need two values that multiply to -6 and that add to -1. So this could be, I think, -3 and +2, right? Because -3 times 2 equals -6, and -3 plus 2 equals -1. So that should work. I can then write this down as, I don't know why I'm drawing a blank there, t minus 3, t plus 2, and that's it. That one's not super complicated, so let's move this one aside as well. But I can write down this new factorization. So t minus 3, t plus 2. Yeah, this function is going to be decently complex, so we'll tell you that much. So, again, all I'm doing is I mean, genuinely, when I tell you, on my other monitor, you can't see my other monitor, on this monitor where my hand is off camera, I have the list of things I wrote down in my packet on page 2, and I'm just going through that list. All right, next thing is to cancel any terms you can. Any factors completely removed will be a whole. I can't cancel anything here, right? I've got a 2t minus 5 and a t plus 1 on top. I've got nothing that looks like that on the bottom. No cancellations, no wholes. So if I write down holes, none. Okay. Plug the values of any holes into the reduced form. I don't have any of those. Okay. Set the numerator equal to 0 and solve. These will be the zeros of r of x. So I want to plug, well here, let's put zeros. So I know I'm going to be doing that next. I want to take this guy and set it equal to 0. And so if you remember, you know, I can set each of these terms individually equal to 0. And so if I have 2t minus 5 equals 0, I can add the 5 over, I can divide the 2, and I get t equals 5 halves. So that is a 0. And if I solve the other one for 0, well, this one's pretty easy. I set t plus 1 equals to 0, and then I would simply get that t equals negative 1. And I'm kind of running out of room there, but so t equals negative 1. So negative 1 is a 0. Okay. So I'm going to delete this work right here. Well, I really want to keep it on screen, but I'm going to run out of room super fast. Here's what I'll do. Here, let's delete this. Okay. Let's move these guys over here. Let's take this, make it a bit smaller, a lot smaller. Just so we know that this was, there's a big semicolon, just so I know that that's the context of what we were doing. We were setting that equal to 0 and solving, we're finding our zeros. Okay, vertical asymptotes, same exact game, we're just doing this on the denominator. So I set this equal to 0. Hopefully this is pretty easy. We're going to get that t equals 3 and t equals negative 2. And again, let me shrink this guy down and show that this is kind of the context of what we're doing. And again, all I'm doing is I am just following a list of things. I keep saying that a lot, but truly, if there's anything to know about this section, is to know that list. Okay. Find the horizontal asymptote or slant asymptote if either exist. So here's a case where we can actually very easily just look at the original function, right? And some of the other functions, we kind of had to like infer what the power might be, but it's just given to us very explicitly, right? I have a power of 2, I have a power of 2 in the original function. And so because those powers are equal, I want to divide their coefficients. So 2t squared over t squared, right? Their coefficients are just 2. And so the horizontal asymptote is going to be y equals 2. Okay. Then what else do we have to do? We have to set x equals to 0 and find the y-intercept. So if we do this, okay, we might not get the nicest answer in the world. This is actually another example of where we kind of want to use the original function versus the reduced function. Because take a look at what happens. If I have this, let me use different colors because I'm getting crammed. If I take this guy, and I set t equals to 0, a whole bunch of stuff is going to disappear immediately. I mean, that has a t, because anything times 0 is 0. That goes away, that goes away, that goes away, that goes away. So what are we left with? Well, we're left with negative 5 over negative 6, which equals positive 5 over 6. So positive 5 over 6 is going to be our y-intercept. Okay. I need to make room. So this guy is going, I'm sorry, and this guy is going, I'm sorry. These guys are getting moved over. Okay. We're still not done yet, though. we're still going. We need to make a sign diagram. So here's what I'm going to do now. I'm going to remove more stuff because I'm really trying to keep this all on one page, but that might not be realistic. These guys are going to have to go. I'm so sorry. Trust me on my factorization. But these can go over here. And now let's draw our sign diagram. So I can draw a line going across like this, and then I want to place down all of my relevant values. So I have 4 of them, and I want to go in order from negative to positive. And that sounds obvious, but it's easy to mess up sometimes. So first value is -2. That's an asymptote. My next value is -1, and that's a 0. My next value is 5/2, and that's a 0. And my last value is 3, and that's an asymptote. And so now what we can do is we can start drawing the lines on this guy, and what you might notice is that every single term is associated with a positive linear line. Now, the one that might be like a little questionable is this point right here, 5/2, because it comes from the term 2t minus 5. And you might think, does that coefficient of 2 change the way things work? And the answer is no, because we're maintaining the fact that we're positive at one side of that line, negative at the other. It doesn't matter how steep it is, we just care if it's positive or negative. So we'll be drawing the same exact line. They're all positive linear. So we can go through, draw our lines. And please, someone stop me if you need a brief sign diagram review. I'm kind of assuming we're getting better at this point, but I'm more than happy to go ahead and explain. All right, so this interval here gets a negative value, negative value, negative value, negative value. 4 negatives, or in fact an even number of negatives, is always going to be positive. So this interval is positive. I will let you in on a trade secret. If all of the lines are positive and linear, it's going to perfectly alternate, right? If you don't believe me, you can try it. This interval gets 1 positive, 3 negatives. 2 of those negatives combine to being a positive, but I still have 1 left over, so that's negative. This is positive, negative, positive. And you can verify that on your own if need be. Okay. So I'm going to make this guy a little bit smaller just to move him over here. Because now let's actually start graphing this, right? And so I'm trying to make room. Let me make this text a little bit smaller as well, just to keep myself organized. Okay. All right. I think this is enough. I think I've done enough organizing. Okay. Now let's start drawing this function. Okay. All right. So let's start marking down all the information. What kind of tick marks will I need? It looks like I'll probably want a little more than 3 this time, just because I have values that go up to 3 and I want to know what happens around those points. But let's go through. So no holes, so we're good there. 2 zeros. I have a 0 at -1 and at 5 halves, which if you did not know, 5 halves equals 2.5. So I can put another 0 at 2.5. We have, actually, I should do this in yellow. I should really, I should do my information in yellow just so it's very clear. So 2.5, okay. Then vertical asymptotes, I have 1 at t equals 3. So that's going to be right here. And then I have 1 at t equals -2. So that's right here. Okay, that is just so slightly off. I need to read that. I'm so sorry. Okay. And then we have a horizontal asymptote at y equals 2. I'm really hoping I got all this right. I mean, again, you're giving me a problem from the textbook. I could be butchering something. I really hope I'm not doing that. Okay, we have a y-intercept at 5 over 6. Now what is that going to be? It was going to be a little less than 1. I don't know what's the exact example. This is so embarrassing. Math major looking up how to... 0.83. So that's going to be like, I don't know. Whoops. Somewhere around here. It doesn't got to be perfect. Honestly, in years past, I used to skip doing y-intercepts because, I don't know, I just thought it was like goofy. I don't really care much about it. I know professors care about them, so I put them in there. Okay. So we have our information. Now, there's a lot going on here, but we can still just follow those rules, or not follow the rules, but look at our sign diagram and just think about what's going on, right? So let's start with the interval from negative infinity to negative 2. That interval must be always positive. So hopefully it's not too crazy yet for me to say that this, hold on, drawing that horribly. This is going to look something like this, right? It's going to start off on the vertical or on the horizontal asymptote, and as it approaches that vertical asymptote, it's going to go off to infinity. Hopefully that's not too crazy. Okay. And now let me cheat temporarily. I'm going to skip that center interval because there's a lot going on in that center interval. So let's skip the interval from 3 to infinity. That has to stay positive. And so hopefully it's not too crazy for me to draw my line here and kind of have, I need to, it's hard to keep a steady hand sometimes, and go out in that direction. So, I mean, I guess here I can move over like this, but hopefully it's pretty clear what I'm doing. Now, what's going to happen in that center interval? Okay, so from the interval negative 2 to negative 1, so from negative 2, which occurs way down there, which you cannot see, from that asymptote to negative 1, I have to stay negative, so I'm keeping that in mind. From that negative 1 to positive 5 over 2, so from negative 1 to that guy, I have to be positive, and then we're also going to be crossing my vertical asymptote at some point. And then from 5 over 2 to 3, we have to be negative. So it's going to look really extreme, but bear with me. So from the asymptote to negative 1, I'm staying negative. So I'm starting down here. I am moving upwards, close to that asymptote, and then I'm going to kind of trail off and touch my 0. The textbook shows the top right one crosses the horizontal asymptote. The top right one crosses the horizontal asymptote. Let me check this really quickly. Because there might be something I'm missing, or maybe, yeah, who knows. Yeah, I think you're right. Yeah. Is there a way we can find this out? I'm trying to think. We have a horizontal asymptote, and then we're staying positive. This is why you were confused about the problem. Oh, okay, okay. Hopefully I wasn't just wasting too much of your time going through all of this. Okay, well, assuming that's what you're confused on, because I will have to take a closer look into this too. This is this behavior here. Okay. How do we see that? That's very interesting. Well, one option, and this isn't like a great, so I wouldn't want to do this. What we could do is we could set our function equal to our asymptote and solve, but that seems like we're doing a little too much, is a nice way to say it. Like okay, this is why, may I ask, did, hold on. You did it with your professor. Was this like a example problem? Do you know what your professor did? Because if your professor just pulled it off the top of his head, then I'm extra confused. I mean, there should be a way we can find this out. And I mean, I could tell you, if you set the function equal to 2 and you solve, you would get an intersection point. But I'm trying to see if there's an easier way we can do this, because that seems like overkill during an exam, if that makes sense. So just give me a moment. I'm trying to see. Okay, so hold on. I might be getting closer. We use the really big plus, really big minus, really small plus, really small minus, and plugged it in. Okay, so I think if I'm getting like how the textbook shows it. Like how the textbook shows it. And then, okay. It approaches to... Yeah, but then the thing that I find interesting is what tips us off that there's an intersection at that point. That's what I'm trying to figure out. So give me a moment. Yeah, that's, I mean, your question is the exact same as mine. So I'm trying, just give me a moment. I'm trying to see what's going on here. Wait. Hold on. Oh, that's interesting. That is interesting. Okay. So, all right, here's an advantage of, yeah, I can show you the thought process. So, okay. Let me make some new space. So, oh, did I just lose the problem? Okay, no, I have it over here. I'm gonna rewrite this down. Let's focus just on end behavior. So, here's the thought process that they're using. Minus t minus 6. Okay, so when you're analyzing end behavior in the function, that is the end behavior. Let me rewind. What you're asking yourself is, as x approaches plus or minus infinity, what's going to happen to my function, right? So I want to ask two questions. Question 1 will be, as x approaches positive infinity, what happens to my function? Or I shouldn't say equal, I should say approaches, right? F of x approaches something, don't know yet. Excuse me. And then as x approaches negative infinity, my function does something. Should not say equals, I should say approaches. That's covered up by chat, but don't worry, I'll move in a second. We're going to focus on this side first. So the horizontal asymptote is going to tell you your end behavior, right? If we look back at this picture, and again, my admittedly incorrect picture, the end behavior is going to be, well, the function is going to approach 2 because of that asymptote, right? So I know right away I can fill in these bits of information. So I can say, as I go to positive infinity, my function approaches 2, and as I go to negative infinity, my function approaches 2. But what we want to see is what's going to happen right before that. And so the way that they're doing this is they're kind of thinking like, okay, what is my function going to look like? Like, what is the output of the function going to look like really, 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 really far away? And so what we're doing is we're kind of just, like, it's kind of, I don't know, you'll see what I mean. So what we're going to say is that if I have my function, right, I mean this guy right here, I have it written down. what's my behavior going to look like if x gets really, really large? And so part of the way we can do this is, I want to make sure I'm not going to, I don't want to, I'm trying to let you know my thought process. I'm treading a very thin line between going into calculus territory and staying into pre-calculus territory. So I'm really trying to stay in pre-calculus territory right now. Let's think of like some massive, massive, huge number, right? So 2 times, what I want to title. I'm gonna use capital B for a billion because that's like their example in the book. So capital B, because I don't want to write out a billion, right? Minus 3 times capital B minus 5 over, let's stick with this for now. Let's just stick with this for now. Okay. And so this is where we get very hand-wavy, but let's think. If I've got 2 times a billion squared, positive billion squared, because we're dealing with positive infinity right now. 2 times a positive billion squared. That's a positive number. It's very, very, very large, right? Okay, so what I know this is we'll say very large, this is very silly, very large positive number, okay? Now, I'm going to be subtracting 3 times a billion. Now, negative 3 times a billion is a large number, and it's a large negative number, but hopefully I'm clear enough in saying that 2 times a billion squared is a larger number than negative 3 billion. Hopefully that makes sense. And this is kind of why I don't really go over this method. So when I ask for the behavior, this is when we perform the steps. Yeah, so if you're looking at n behavior, if they were going to say, like, what does n behavior, the function, look like? Well, okay, let me rewind. If you were simply asked to write n behavior and nothing else, you can just get away with the blue and the green that I wrote up top, just using the fact about the horizontal asymptote. But what we're trying to analyze right here is how do we tell when we have an intersection on the horizontal asymptote that's not immediately obvious. And anyway, back to what I was saying. Right, we have very large positive number versus just a normally large negative number. And when you subtract that large negative off of a huge positive, you're still going to get large positive number. And then hopefully it's not too much of a stretch to believe that a very large positive number minus 5 is still a very large positive number. So all of that put together, what we can say we know so far is that in the blue case, and here I'll do it in blue just so we know we're doing the blue case, the numerator is a large positive. That's what we know so far. We still have to do the denominator. So my denominator is t squared minus t minus 6. And so if we say, okay, we get billion squared minus billion minus 6. A billion squared is going to be huge and positive. So huge plus from this guy. We're going to be subtracting off a billion, but a billion squared is like so inconceivably big that that subtraction of a billion doesn't really matter, right? So I'll say a large negative, but when I subtract these, we still get a large positive. Minus 6 is still a large positive. Did I get something wrong? Please tell me I didn't get something wrong. Give me one moment. I just want to check. Okay, hold on. Wait, why? Please give me one moment. Please give me one moment. Oh boy. Okay. 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 I've got it now. Thank you for bearing with me. Okay. So, we know that we have a large positive over a large positive. And I'm probably, okay, here's what I'm going to do. I'm probably just going to handle the blue case. You can handle the green case similarly, but it's getting kind of late, and I'm very hot right now. But I will finish off with the blue case, and I'll try and offer you the best explanation I can offer. But this is the exact same, actually, really quick. The one difference between the green case, where I go to negative infinity, is instead of plugging in a positive billion, you're plugging in a negative billion, or a negative huge number, right? But it works the exact same. So now what I know here is that this entire function at the value of some huge positive number is some very, very small positive number. And the reason for saying this is a very small positive number is because when you get into this idea of like taking some incredibly large positive number but also dividing it by an incredibly large positive number, it's going to be a really small positive number. I'm trying to think of a more intuitive way to explain this. It's like saying that if I had 100,000 divided by 999,999, or 99, right? If I took this fraction right here, this is going to be an incredibly small positive number. And you can plug that into your calculator to kind of justify that to you. This is where I'm really treading the line between going into calculus stuff. I'm really trying to keep this as down to earth as possible. But hopefully I'm believable enough when I say that I can infer that when I have some huge positive number divided by some huge positive number, they're both going to tend towards a really small, still positive number, right? Okay. Hopefully I am somewhat justified in saying that. I know that might not be the most satisfying conclusion in the world. But where are we going with this? So we know that as we go to infinity, and I'm going to keep scrolling and draw you a picture, we know that on our function, and we have some huge asymptote. When did math become fake? LOL. I'm going to tell you what they don't want you to hear. It's always been fake. None of it's real. Okay. Pet peeve for a second. This is the one reason I kind of don't like discussing this stuff in my sessions, is because these are really topics that, and I get why they're introducing it to you. It's good to like get this in your brain, but this feels fake because it's really hard to like justify why we're doing this without showing you calculus. And that's why I'm having this mental struggle of I don't want to go into calculus topics, but like it's not until calculus that you get into this idea of what happens as these numbers get really big, and then you justify it with actual not fake math. And so it feels very fake right now because I have to dance around this idea of not showing you the things that you haven't learned yet. But anyway, we have our horizontal asymptote at 2. And so we know that way, way out towards infinity, so, or not even infinity, let's just consider this to be the billion x value, right? What I know is that my function is going to have behavior over here. It's going to be getting very, 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 very close to my asymptote. Like incredibly close. If I had like my zoom lens on right here, and I'm kind of zooming in on the behavior, I have this asymptote, and you have like hardly any difference between what's going on, right? And so I know that I can find out the location of that point by thinking about the difference between the asymptote and my function. Hopefully I didn't lose anybody in saying that. But like, think about what's going on. I have some function value that is like getting really, really close to 2. Or like the... Yeah, how do I want to... Anyway. We're getting very, very, very close to 2. But the function value is not quite going to be 2. It's going to be 2 minus the value of the function. I can kind of like take the difference. If I subtract off my function value, I can kind of compare it to where 2 is existing. And anyway, the intuition comes in. I'm going to try and wrap this up and stop waving my hands in the air. The intuition comes in is that because we're able to identify the fact that this is a very small positive number, and I know this gets super, super, super close to 2, I can say that 2 minus an extremely small positive number is going to be just below 2 at that point. Wouldn't it cross the horizontal asymptote and get really close to the x-axis? No. You got to be careful here, because it's going to be glued to that asymptote, and in our case here, the asymptote is not the x-axis. So even if it crosses that asymptote at a certain point, and I think the textbook leaves it kind of ambiguous of where it actually crosses, because yeah, they have a more specific way of doing it. I'd have to look into it, but we're dragging on this problem for quite a while. But it doesn't approach the x-axis. It's always whether or not it crosses that asymptote. As we get towards very large values of x, it's always going to be very, very close to that asymptote, right? But what our intuition here is that if I take that asymptote of 2, you can almost think of 2 as like the function at infinity. That's really bad math. Like I shouldn't be writing that. But just think of it like the function at infinity just equals 2. And then think of this really small positive value as thinking of like, what's the function at a very, very large number, but not infinity? This would be like minus the function at 1 billion, right? And if I'm looking for the difference between the function at infinity and the function at 1 billion, when I subtract off that real small number, yeah, okay, I get your question, and now like I sort of see where the confusion comes from. It's a really, really small number away from 2. It's not a really, really small positive number away from the x-axis, and that's why I think you're getting confused. This is a good question, but I feel like, okay, isn't this the section the textbook shows crossing the horizontal? This is the section. Okay. Here's what I'll say. I will probably need time to think about a better way to explain this. Like, I'm sure I can come up with a much nicer sounding explanation, but right now, I'm a little too caught off guard to give you an explanation that's not going to be very technical and very confusing. So, would I be able to tell you to try talking to me either before or after my session tomorrow, and maybe we can look at this a little closer and I can try and get you a better explanation, because right now I think I'm just struggling to find the words to kind of explain this, if that makes sense. And I'm sorry I wasn't able to give you a great explanation, but hopefully, maybe, I don't know. We'll see. I know chat probably has latency, but trying to look at the textbook. Sometimes I arrive as early as 5 p.m. That's a little extreme, but like around like 5:15, 5:20, I'm usually around by then. I do have an exam tomorrow, so I can't promise a ton of my time, because I might be cramming for that, but I will try and give it some thought and try and think of a better way to explain this to you. But yeah, if you come like half an hour before, should be around. Yeah. Oh, okay. I see where they're going with this, but I still want time to think about it. So try me again tomorrow. But I think I might have a better explanation for you tomorrow. I'm just very overheated, and give me some time to think about it. Anyway, yeah. Amelia, thank you so much for all of your messages in the chat and participation. I'm very happy that you and Madeline, very happy that both of you found this very helpful. I'm glad that you showed up. I'm glad this could help at least two of you. So thank you very much. Otherwise, I need to go eat dinner. I need to turn my fan on. Show up early to my session tomorrow or show up late, but I will be around then. Thank you guys so much. I need to head out now, but I'll see y'all later.